Hi, Mr. Richards here. Today's lesson is on graphing quadratic functions. It's our first in Chapter 9. We have some vocabulary that we need to get down first before we go through our examples. So first off, let's start with what quadratic functions are. Well, quadratic functions are non-linear. Meaning they're not going to be in a line. And the standard form of a quadratic function is f of x equals ax squared plus bx plus c as long as a is not equal to 0. Now, what is a parabola? Well, it's the shape of the graph of a quadratic function and if you're looking for an example of a parabola, you have one down here in blue in our key concept box. And the axis of symmetry is a vertical line containing the vertex of a parabola. And it's good to know that parabolas are symmetric around this central line. And if you look at the key concept box, we have our axis of symmetry as this red dotted line. You can see how the parabola is symmetric around this, which will help us when it comes to graphing these things. And it does contain the vertex of the parabola, which leads us into the definition of vertex. The vertex is the maximum or minimum point of a parabola. And it is where the axis of symmetry intersects the parabola. And it's good to know that it's the only point that it does that. Now, when it comes to maximums and minimums, we'll have a minimum when you look at the standard form of ax squared plus bx plus c, we will have a minimum when a is greater than 0. We'll have an upward graph, and that graph will look something like this. So you'll have a vertex here, and that point represents the minimum. Now compare that to maximum. We'll have a being less than 0. And this will be a downward graph, such that when I look at it on a graph, it would be something like this, where I have my vertex, and the point represents the maximum of the graph, whereas this point was the minimum. So now that we're squared away with our vocabulary, we can get started with our examples. In our first example, we're going to use a table of values to graph y equals x squared plus 2x plus 3, and we'll state the domain and range. Well, it's good to know here as we look at this form that our a here is a 1, which is a positive number, so we should expect an upward graph. So as I make my table of values, I can just make a basic function table or XY chart. And we get to pick in the numbers we'd like for x. And let's just pick one and say, all right, what happens when I put -3 in for x? Well, -3 squared is 9. -3 times 2 is a -6, so 9 minus 6. And then we have our plus 3, which gives us a y of 6. So -3, 6, so right here. Then if we look at -2 for an x, -2 squared is 4. 2 times -2 is a -4, plus our 3 gives us 3. So we'll have -2 for x, 3 for y. What about -1? -1 squared is 1, minus 2 plus 3 gets us 2. So -1 and 2 is right there. We'll have to extend our function table here a little bit, as we have 0 now for x. Well, 0 squared is 0, plus 2 times 0 is 0, plus 3, so 0 is going back up to 3. Next we have 1. 1 squared is 1. 2 times 1 is 2, plus 3 gets us 6 again. 1, 6. Well, there's my points that I need. And so as I go in now to draw in our line to graph this, we'll want to do so it's curved at the bottom and coming back up in a curve-like shape. And drawing in our arrows. Don't draw this rigid as in 2 lines. Just make it a nice curved graph. Now our domain, our values of x's. Remember, our domain are our values of x's. Our domain here can be all real numbers. And our range, the range is a little different. The range are our values of y. Well, we certainly have a minimum here. We have a minimum of 2. And so our range is going to be pretty much all numbers. So we'll say all numbers for y, as long as y is greater than or equal to that 2. In our second example, we need to find the vertex, the equation of the axis of symmetry, and the y-intercept for each graph. Well, our vertex is going to be down here, and so our vertex is indeed right there. And so we can say that our vertex is at 2, -2. What about our axis of symmetry? Well, that would be right around here, and it goes through our vertex, so we can draw in fact, a dotted line here, or a dashed line that goes through. We can label that our axis of symmetry. And when we think about an equation for this line, it's where all the x's are equal to 2. And lastly, we have our y-intercept. Our y-intercept is where the graph crosses the y-axis, which is right there. So the y-intercept is at the point 0, 2, which you can also just call 2. Once again, we're asked to find the vertex, the equation of the axis of symmetry, and the y-intercept of each graph in example 2b here. Well, our vertex is here. So our vertex is at the point 2, 4. And then for our axis of symmetry, this is the dotted line that goes through the vertex, which is right here, where our parabola is symmetrical around. And the equation of that line, similar to our last example, is x equals 2. Now lastly, for my y-intercept, this is down here. At 0, negative 4, which I can also just call negative 4. In our example 3a, we're asked to find the vertex, the equation of the axis of symmetry, and the y-intercept given an equation and not a graph. Well, if we think about the standard form of a quadratic function, that is y, or f of x, equals ax squared plus bx plus c. Now, our a here, in this example, is negative 2. Our b is equal to negative 8. And our c is also equal to negative 2. And we're going to use those now to calculate these. And we will actually start with the axis of symmetry. Now the formula for the axis of symmetry can be found down here, which is x equals negative of b over 2a. Now for our solving purposes, we can say x equals the negative of b over 2a. I can just put that negative with the b, and it'll make it a little bit easier to calculate. So we'll have x equals the negative of negative 8, which is just a positive 8, over 2 times negative 2. Well, that gets me x equals 8 over negative 4, which means x equals negative 2. So the axis of symmetry is x equals negative 2. What about the vertex? Well, to find the vertex, use this value that we found for the axis of symmetry as the x-coordinate of the vertex. To find the y-coordinate, we'll substitute that value for x in the original equation. So we'll take our y equals negative 2x squared minus 8x minus 2, and we'll put in negative 2 each time we have the x. So y equals negative 2 times negative 2 squared minus 8 times negative 2 minus 2. Y then equals negative 2 times 4, and then negative 8 times negative 2 is plus 16 minus 2. Y equals negative 8 plus 16 minus 2. Y equals 8 minus 2. Y equals 6. Well then, the vertex, using the x and y, are at negative 2, 6. And that is my vertex. Now, there are two ways to get to the y-intercept. The y-intercept is when x equals 0. It's where it crosses the y-axis. So if I use my original formula, y equals negative 2x squared minus 8x minus 2, and put zeros in for x, I would get y equals, well, we'll just put it in, I guess. 0 minus 0 minus 2, y is going to equal negative 2, which means my y-intercept equals negative 2. And that's one way of solving it. The other way is recognizing, well, my y-intercept in the standard form of a quadratic function is c. Well, if I look back at what my c was, it was negative 2. And sure enough, it was. So that's how we can find the vertex, the equation of the axis of symmetry, and the y-intercept of a quadratic function just given the function itself. And if we practice this now one more time, let's remember that the standard form of a quadratic function is y equals ax squared plus bx plus c. So here my a is equal to 3, my b is equal to 6, and my c is equal to negative 2. And so if we start off once again by trying to find the axis of symmetry, we'll pull this formula one more time, not last time, but certainly one more time. X equals negative b over 2a. X is going to equal negative 6 over 2 times 3. And so x will equal negative 6 divided by 6, which is negative 1. So the equation for the axis of symmetry is x equals negative 1. What about now my vertex? We'll use the original function, y equals 3x squared plus 6x minus 2. We'll substitute in negative 1 for each of the x's, so y is going to equal 3 times negative 1 squared plus 6 times negative 1 minus 2. So y will equal 3 times 1 minus 6 minus 2. So we'll have 3 minus 6 minus 2, which is negative 3 minus 2, which is negative 5. And so my vertex can be found using the x and the y at negative 1, negative 5. And lastly, for my y-intercept, we could go through our original function one more time. Y equals 3x squared plus 6x minus 2. And almost mentally, if you put in 0 for each of the x's, you'll end up with y equals negative 2 for your y-intercept. Or, just like in the last example, we could recognize that, hey, my c is the y-intercept in a standard form of a quadratic function. And so negative 2 is going to be my y-intercept. So now we'll consider in example 4, f of x equals negative x squared minus 2x minus 2. Well, if we remember that the standard form of a quadratic function is f of x equals ax squared plus bx plus c, we can define our a as negative 1, our b as negative 2, and also our c as negative 2 here. So when we go to determine whether the function has a maximum or minimum value, what we can do is say, well, my a is equal to negative 1. And if we remember from our first page, when our a is less than 0, we are going to have a parabola that opens downward and has a maximum. I mean, if you just think about a graph that's going to open downward, any kind of graph that opens downward, The minimums, well, you don't know. It just keeps going forever. But you do have a maximum point. And so that's why we can say that this is a maximum. Then state the maximum or minimum value of the function. Well, if we remember that the axis of symmetry goes through the vertex, we can use that formula of negative b over 2a to find where that axis of symmetry is. Well, if we substitute in now, negative 2 for b, so the negative of negative 2 is 2 over 2 times negative 1, we'll end up with 2 over negative 2, which is simply negative 1. And once we have that negative 1, we need to plug it back into our original function. So negative x squared minus 2x minus 2, and we'll substitute in the negative 1. So the negative 1 squared minus 2 times negative 1 minus 2. Negative 1 squared is 1, but the negative of that is negative 1, plus 2 minus 2, and this equals, coincidentally, negative 1. So if we were finding our vertex, the vertex would be at negative 1, but all we're interested in is that y value of negative 1. So our maximum is negative 1. Now what about the domain and the range? Well, the domain is the set of all the x values. And here there are no restrictions on that. So our domain we can list as all real numbers. Our range, there is a restriction. We have in this question a maximum of negative 1. And so we're going to write for this all real numbers less than or equal to the maximum value of negative 1. And if we wanted to write this in the correct notation, we could write with a little bracket thingy, y is less than or equal to negative 1. So now we come to example 5, which is kind of the culmination of this entire lesson, where we'll graph quadratic functions not by using a table of values as we did in our first examples, but using these 5 steps. First, to find the equation of the axis of symmetry, then to find the vertex and determine whether it's a maximum or minimum. We'll find the y-intercept. We'll use symmetry to find additional points on the graph if necessary, and then we'll connect the points with a smooth curve. And so, if we look at this question, our a is equal to negative 1, our b is equal to 5, and our c is equal to negative 2. And so now first we will find the axis of symmetry. And we will once again use the formula x equals negative b over 2a. And so b is 5, so I can write that as negative 5 over 2 times negative 1, which is negative 5 over negative 2, which is negative divided by a negative is positive 5 halves, which is the same thing as 2.5, 2.5, 2 5/10. And so that'll be my axis of symmetry, which I can draw on my graph right now at 2.5. So x equals 2.5, or 2 5/10, is my axis of symmetry. Next, step 2 is to find the vertex. So we'll use our original equation, f of x equals negative x squared plus 5x minus 2. And we'll put in the 2 and 5/10. So this will equal negative 2 and 5/10 squared plus 5 times 2 and 5/10 minus 2. Well, we'll have a negative 6 and 25/100 plus 12 and 5/10 minus 2. And that will result in 4 and 25/100. So my y equals 4 and 25/100. So my vertex will be at the point 2.5, 4.25, which we can draw on our graph right about here. So, the last part of this is finding whether it's a maximum or a minimum. And if we look at our A is equal to negative 1, which means that we're going to have a downward graph, so that the vertex is going to equal a maximum. Now, step 3, Y-intercept. Again, technically we're supposed to look at our negative x squared plus 5x minus 2, and technically it's where our x equals 0, so we would have 0 plus 0 minus 2, and so that our y-intercept is going to be negative 2. Or we could just look at our c here and see that it's negative 2. So the y-intercept is at negative 2. Which, if you remember, is at the point 0, negative 2. So I can draw 0, negative 2 now as my y-intercept. And now it comes time to try to find other points. And this is where it gets to be a little bit fun. This is called an axis of symmetry for a reason. Because if we look here at this point at 0, negative 2, I should expect another point on this side of the graph that is equal distance away in line from this axis of symmetry. Well, right now I have the point 0, negative 2. Well, right now 0, negative 2 is 2.5 spots away from that axis of symmetry. So we need to go 2.5 spots on the other side, which leaves us with 5, negative 2. And so I can plot a point at 5, negative 2. Next, we should look to fill in our graph either somewhere over here or over here. I'm going to pick the point 4, where x is 4, and see where my y falls. Probably somewhere in this area, but let's see what happens. So if x is 4, and I put that 4 in, it would be negative 4 squared plus 5 times 4 minus 2, which would be negative 16 plus 20 minus 2, which is just 2. So that's going to be at the point then 4, 2, which if I graph is going to be right there. And again, I can use the axis of symmetry now to graph a point on this side. Right now this is 1.5 spots away from my axis of symmetry. So I need to be 1.5 spots away on the other side, which is right here, which is at the point 1, 2. And now that I have these points, I can draw in my curved parabola. Looks a little bit like this. And that is how I can graph a quadratic function using the axis of symmetry, vertex, y-intercept, and other points. Now last in our lesson of graphing quadratic functions, we get to tie it all together with the word problem. Ben shoots an arrow. The path of the arrow can be modeled by y equals negative 16x squared plus 100x plus 4, where y represents the height in feet of the arrow x seconds after it is shot in the air. Our first step A is to graph the height of the arrow. So I'm going to rewrite my equation here. Y equals negative 16x squared plus 100x plus 4. And if I define my ABC, my A is negative 16, the B is 100, and the C is 4. And we're going to follow the same steps we graphed in example 5 to graph this. And so we'll start off with the axis of symmetry. And if I use my formula here, x equals negative b over 2a, this would be negative 100 over 2 times negative 16. Well, this is negative 100 over negative 32, which is a positive, if you divide by negative 4 on top and bottom, 25/8. Now, if you want to work with the 25/8 in this problem, you can, but I'm going to work with these as decimals on this example. So my axis of symmetry, I'm going to call 3.125 equals x. And that's what I'm going to use for my axis of symmetry in this question. So I'm going to go ahead and graph that in as close as I can. And so there is my axis of symmetry. Next step, find the vertex. Well, in order to find that, we'll use our original equation, which is y equals negative 16x squared plus 100x plus 4. And we'll substitute in the 3 and 125 thousandths for each of the x's. So y is going to equal negative 16 times 3.125 squared plus 100 times 3.125 plus 4. So y is going to equal negative 156 and 25 hundredths plus 312 and 5 tenths plus 4. Add those all together, and we get 160 and 25 hundredths. So my vertex, I can list as 3 and 125 thousandths and 160 and 25 hundredths. And so now it comes time to put this on our graph, and so I'm going to use my y-axis by counting up by 20. So 20, 40, 60, 80, and so on. And on my x-axis, I was counting up by ones. And that was in seconds on the x-axis. And the y was in feet, or the height in feet at least. And so now as I go to graph 3 and 125 thousandths is 160 and 25 hundredths. That's going to be right around here. And there's my vertex. Next, let's go ahead and look for our y-intercept. And our y-intercept, if you put 0 into the equation, or if you just notice that c is equal to 4, the y-intercept is going to be 4. And so, we can draw that in now as well. Now, we're left to do other points. Well, if we start off by knowing that 0, 4 is our y-intercept, what is the other point that's going to be there on the other side of the axis of symmetry? Well, right now, the distance from here to here is 3 and 125 thousandths. So from this imaginary point over here, we have to go another 3 and 125 thousandths. So if we look at where it would be on the axis of symmetry going straight across, that would be at the point 3 and 125 thousandths, 4. Well, that again there is halfway to where we need to go, so we need to add another 3 and 125 thousandths to that, which would get us to 6 and 25 hundredths, 4. And if I graph that at 6 and 125 thousandths and 4, that would be somewhere right around here. Again, the axis of symmetry puts these equal distances away from the axis itself. Now, if we're looking for one more point, let's see what happens to our y in feet when x equals 1. Well, if we put 1 into this equation, that would be negative 16 times 1 squared plus 100 times 1 plus 4, which gets me negative 16 plus 100 plus 4, which when it's all said and done is 88. So that's the point 1, 88, which on the graph is right about here. And now to find our last point, it needs to be on the other side of the axis of symmetry. Right now, I'm 2 and 125 thousandths units away, so I need to be 2 and 125 units away from the axis of symmetry. So if I take 3.125 and I add 2.125 to that, that distance ends up being 5.25. So the other matching point now is going to be at 5.125 and, running out of room there, 88. So 5.125, 88 is somewhere right in this neck of the woods. And now, my last step, I can draw in this curve. And that's my graph. Now, at what height was the arrow shot? There we want to look for our time when time was 0. So we're looking for when x was 0, which is the same thing as our y-intercept, which ended up being at 4 feet. And what was the maximum height of the arrow? Well, that would be at our vertex. And this maximum height was 160 and 25 hundredths feet, and that was at the time that it was 3 and 125 thousandths seconds. And that is it for this lesson on graphing quadratic functions. Good luck.